Electronic ignition systems use the input from engine sensors to determine the spark timing. Electronic ignition systems use a transistor known as an NPN, or negative-positive-negative transistor, to switch the primary circuit of the coil on and off. The transistor's emitter is connected to ground. The collector is connected to the negative terminal of the coil. When a small amount of current is supplied to the base of the switching transistor, current flows through the transistor and the primary coil windings. When the current flow to the base of the transistor is interrupted, the transistor blocks the flow of current through the emitter and collector, effectively opening the primary circuit. The dwell, or the amount of time that current needs to flow through the primary circuit to saturate the iron core, is controlled by the switching of the transistor. The use of electronics to monitor engine operating conditions and to switch the primary circuit has led to the development of distributor-less ignition systems. Distributor-less ignition systems offer the advantage of reducing engine friction, as the load on the camshaft that was necessary to drive a distributor is eliminated. Distributor-less systems use an ignition coil or coils to provide spark directly to the ignition cables and spark plugs. On most distributor-less systems, one coil is used to provide spark for 2 cylinders, although variations are common. On distributor-less ignition systems, each coil has an ignition module with a transistorized switch that is controlled by the powertrain control module. The powertrain control module uses the input from an engine position sensor to supply or stop current flow to the ignition module that completes or interrupts the primary circuit of each ignition coil. Whether or not a distributor is used, the time that the primary circuit for each coil must be opened and closed is directly related to the position of the piston in the cylinder and the engine stroke that the piston is on. The position of the crankshaft is used to control the flow of current to the base of the switching transistor for each coil. A number of different types of sensors are used to monitor the position of the crankshaft. These sensors can include magnetic pulse generating sensors, metal detection sensors, Hall effect sensors, and photoelectric sensors. The mounting location of the sensors depends on the design of the ignition system. On distributor-based systems, the sensors can be mounted in the distributor, or they can be located on the crankshaft near the harmonic balancer. By far, the most common type of crankshaft position sensor in use on today's vehicles is the magnetic pulse generating sensor. Magnetic pulse generators use a timing disc and a pickup coil to send a voltage to either the ignition module on older systems or to the powertrain control module on current systems. The pickup coil operates on the principle of electromagnetic induction that says voltage can be induced when a conductor moves through a magnetic field. A permanent magnet in the pickup coil is used to create a magnetic field. A rotating toothed disc attached to the crankshaft or distributor shaft moves through the magnetic field of the pickup coil. As a tooth on the rotating wheel passes through the magnetic field of the sensor, an alternating current voltage is induced in the wire to the control unit. The alternating current is a positive voltage as the tooth approaches the pickup, then switches to 0 as the tooth is aligned with the coil, and then goes to negative as the tooth moves away from the pickup coil. The number of teeth on the crankshaft rotating wheel are equally spaced in terms of the degrees of crankshaft rotation. The number of teeth on the crankshaft rotating disc vary by the design of the system from 12 to 48. Most designs have one missing tooth that indicates the position of the number 1 cylinder at top dead center. Where the magnetic pulse generating sensors are mounted in the distributor, there is typically one tooth for each cylinder. Hall effect sensors are currently the most common type of camshaft position sensor on today's vehicles. This type of sensor became popular as a distributor-based crankshaft position sensor in the early 1980s. A Hall effect sensor produces an accurate voltage signal throughout the entire RPM range. The Hall effect signal is a square wave signal. Square wave signals are often called digital signals because they are either on or off. The Hall effect principle says that if current is allowed to flow through a thin conducting material that is exposed to a magnetic field, a voltage is produced. The Hall effect generator is a thin semiconductor layer that has two terminals for positive and negative. Across from the semiconductor is a permanent magnet. The magnetic lines of flux of the magnet bisect the Hall layer at right angles to current flow. Two additional terminals located on either side of the Hall layer form the signal output circuit. When the shutter allows the magnetic field to reach the Hall layer, the magnetic field expands and the switch generates a very low voltage. When a moving metal shutter plate attracts a magnetic field to pass through the Hall layer, the Hall effect switch produces a voltage signal. The Hall effect circuit uses an amplifier and inverter to change the signal that is sent to the control module. The inverter changes the low signals to high and the high signals to low. When the shutter vane air gap passes in front of the Hall effect sensor, voltage through the circuit decreases. The output signal is changed to a high signal that switches the transistor on, completing the primary circuit for the ignition coil. The dwell of the primary circuit is controlled by the size of the shutter vane. As the vane passes out of the Hall effect sensor, a high voltage is sent from the sensor. That voltage is inverted to a low signal, and current to the base of the transistor is interrupted. With no current to the base of the transistor, the primary circuit is opened, and the voltage is induced into the secondary windings of the coil. On non-computer controlled distributors, timing is advanced by a vacuum advance in response to engine load, and by a centrifugal mechanical advance that works in response to the speed that the distributor shaft rotates at. On computer-controlled systems, both distributor and distributor-less systems, timing advance is calculated by the computer based on the inputs from the different engine sensors. In general terms, timing is advanced during engine warm-up, as engine speed increases, and during increases in engine load. If at any point during normal timing advance detonation is detected, the timing advance is reduced or timing is retarded. Timing is retarded as engine speed decreases, as engine load decreases, when spark knock is detected. By continually adjusting spark timing, the computer-controlled ignition systems can provide for maximum engine power, fuel efficiency, and reduced emissions levels under all operating conditions. In this video, we've looked at the functions of a gasoline engine ignition system and the components in the primary and secondary circuits. Then we looked at the operation of the ignition system in conventional distributor-based ignition systems and on the newer distributorless ignition systems. Finally, we looked at how engine position sensors are used in electronic ignition systems to control the primary circuit of an ignition system. Thanks for watching.